So let's refresh our memories. On the first day of studying atomic and nuclear physics, we identified three big problems in light that classical physics couldn't solve, and one of them was atomic spectra. Here's a picture of a gas spectrum tube. This happens to be helium gas, that when you run a current through it, it gives off this sort of orangey, yellowish, reddish glow. And helium always does this. They couldn't figure out why. It always gives off a very characteristic set of frequencies. This is what's known as its emission. So here's what we call its emission spectrum. If a gas is excited, just a way of saying given energy in some way, only certain characteristic frequencies of light are emitted. It happens always to be the same ones. It's like a fingerprint. You can actually use this to identify what sort of gas you're looking at. In separate experiments, scientists tried it the other way. They had a sample of gas, and they sent white light through it, white being a continuous color spectrum. All the colors are there, and they collected light on the other side, and they found that certain frequencies were absorbed by the gas. They didn't make it through to the other side. This is known as its absorption spectrum. If white light is passed through a gas, only certain characteristic frequencies of light are absorbed. Quick sidebar here, strange peculiarity of the English language. When you take the word absorbed and make it the noun form, the B changes to a P for no good reason. It's not an absorption spectrum, it's absorption spectrum. Don't know why, but it's good to know. Okay, so let's think about for helium what that looks like. Well, you just saw that when you put the current through helium, you saw that sort of reddish orangish glow, but then when you take a diffraction grating and separate the frequencies, this is actually the colors that you see. These colors mixed together made that glow that you saw from the helium spectrum too. And then in the absorption experiment, when you send the white light through and then collect on the other side, all the colors are going to be there except for certain frequencies that are absorbed. They're missing from the spectrum. That's the absorption spectrum for helium. Now take a look at these two. I'll give you a second. You should notice someone. Yeah, you can't miss it. These are the colors that get emitted. These are the colors that are absent from what's absorbed. They match. They're exactly the same. So this characteristic set of frequencies are the exact same whether they're being emitted or absorbed by this particular gas. And this happens for every particular type of gas you can put it through. So here is for nitrogen. These are the colors given off nitrogen. These colors put together make this sort of purplish glow. Here for oxygen, this sort of whitish bluish. You put these colors together, that's what you get. For neon, that's what you see in the neon light, right? This sort of orangey glow. All these colors put together make this orangey glow. Here's for mercury, this very whitish, bluish glow. These colors together, but it's always the same. These are the ones for mercury, these are the ones for neon, or nitrogen, oxygen. You can actually identify these particular materials by this characteristic spectrum. The scientists were baffled. Why does this happen? What could explain this? Well, let's go back to the Bohr model of the atom. So here's our picture, our usual picture of the different orbits of the electrons, which now we're going to call energy levels, because the electrons have different energies in these different levels. But they're the only ones that are allowed by the fact that the angular momentum must be quantized. Anything in between, the electron can't be here, or here, or here, or here, or here, because that's not a stable orbit that won't have the standing wave circle back in on itself and feed the energy back in. These are the ones that are restricted by Bohr's model. Let's zoom in. Closer and closer, right? And the closer we get, the more we can visualize this as reminding ourselves that we first identify the electron as being like a dog stuck in a well, right? Here's the electron, here's like the sides of the well, and here's the electron in like the bottom of the well, the closest to the nuclei where it sort of wants to be, but here's the other places in the well where the electron could possibly be. Let's go back to that dog in the well picture. So here's the dog stuck in the bottom of the well, representing the electron closest to the nucleus of the atom, but now let's say there are some ledges on the well, representing a little section of the energy levels, those orbits of the electron. The dog could be here, or here, or here, or here. Maybe there's a lever on every single one of these ledges. You throw a rock in, and if it's not enough to get the dog out of the well, maybe it gets the dog up to one ledge or another. She jumps up to here. Or maybe she jumps up to here, and then maybe when she jumps back down, she hits the lever and the rock comes back out. Here's the electron. The electron is represented by the dog. The rock is represented by the photon. So you send a photon of light in, and if it's maybe not enough to get the electron out, like in the photoelectric effect experiment, maybe it's enough to just kick it up to this energy level. Or you send another photon in, and it's enough to kick it up to this energy level. Because remember, the photon is just energy. It just needs to have a little bit more energy to get closer to the top of the well, or farther away from the nucleus, or closer to being outside of the atom. This is what's known as an energy level diagram. So these ledges in the well are representative of those energy levels, the orbits in which the electron could possibly exist. Right? These are like the ledges in the well. The electron could be here, or here, or here, but nowhere in between. Just like the dog can't be anywhere in between ledges, because what would that even look like? That would be kind of weird, right? This is known as an energy level diagram, as I said, right? Okay, so let's take the simplest atom possible, the hydrogen atom. The hydrogen atom only has one electron, and it turns out for one electron you can actually develop a mathematical model for the different energies the electron could have at each of these energy levels. It's a relatively simple equation. Here it is. E sub n equals negative 13.6 electron volts over n squared. We're going to go ahead and box that in. N is what's known as the principal quantum number. People taking chemistry should recognize that. And E sub n is the energy of the electron in any of these energy levels, the nth energy level. So the energy here would be E1, this would be E2, E3, E4, and so on and so forth. For any other atom besides hydrogen, though, it turns out the equations are much more complicated. In fact, you need mathematical models, computer models to try to figure out what's going on, and you can't write a very simple equation, so we're not going to deal with that. We're just only going to deal with hydrogen, and we can learn enough about it just from a single electron atom like this. So let's label the energy levels. When the electron's all the way down here, where the dog's in the bottom of the well, that's sort of where it wants to be, the lowest amount of energy possible. That's what's called the ground state. That's n equals 1. And the next energy level up is just n equals 2. That's called the first excited state, because now the electron would have more energy. And when an electron has extra energy, we say it's excited. Just like if a dog jumped up to this ledge over here, she's going to be a little more excited, right? She's a little more dangerous. She's farther away here. Maybe she gets a little nervous. Maybe some nervous, excited energy she has. Here's n equals 3, the second excited state. Then we just keep going. I just don't have a whole lot of room here, but it would be n, 4, 5, and 6, and so on and so forth. We can clearly calculate the values of this by putting in different values of n. So n equals 1, which is going to be negative 13.6. Then just go ahead and calculate for n equals 2 and n equals 3 the values of E sub n. We can label them over here. Real simple calculations. For n equals 2, we're just dividing by 2 squared root of 4, so we get negative 3.4 electron volts. For n equals 3, we're just dividing by 3 squared root of 9, we get negative 1.51 electron volts. Remember, they're all negative because, just like the dog, the electron is stuck there, right? This really represents how much energy it is to get the electron out of the atom. This would be the energy to get the dog out of the well. All of these are what we call transitions. Here, maybe we throw a photon in and the electron transitions up here, just like throwing the rock in. The dog jumps up to a higher energy level. But the electron can only be here or here. If you put another photon, it can only be here, because this represents a little bit of that circular orbit. The electron cannot be anywhere in between. Just like the dog can be here, throw a rock in, the dog can be here, throw another rock in, the dog can be here, but the dog can't be here, because what would that look like? The dog can't just magically float there waiting for another rock. Remember, that was the whole point where the electron, the rocks have to come in chunks of just the right size. But the rocks are photons with very specific energies. And so the change in energy electron comes from a photon whose energy is hf, and since the electron can only change energy from here to here, or from here to here, only certain frequencies of photons will make that happen. If the photon frequency tries to go in here and kick the electron up to this energy here, well, there's no energy level there. It just won't work. It will not get absorbed or emitted. It doesn't work that way. Or if you throw the rock in, it only gets the dog up to here, well, the dog just falls back down, the rock comes back out as if it never went in. And this explains atomic spectra. Only frequencies that match the differences in energies between energy levels will work, either being absorbed or emitted. Okay, so let's say we look at these different types of transitions. Let's say when the electron jumps up. So the electron jumps up by sending a photon in, just like the dog jumps up when you send the rock in. That means it must absorb a photon. Throw the rock in, the rock is now in the well. Again, it's absorbed, right? You can't see the rock anymore. That means the dog jumped up. Put a photon in just the right energy, which means just the right frequency, and it jumps up to a higher energy level. Now, the dog might get a little bit nervous there, so maybe she jumps down. So she jumps down to here, or maybe she jumps all the way down. How does that happen? Well, again, maybe there's a lever there with a rock sitting on a lever. The dog jumps down, hits the lever, and a rock comes out. What's the rock? It's a photon. That means that when an electron jumps down, it emits a photon, because it has now lost energy. It went from negative 1.5 to negative 3.40. It now has less energy. It gives off that energy as a photon. So jumping up is absorbing, jumping down is emitting. And again, it only happens when the transitions are exactly of the right frequencies. So let's say we have an electron in the ground state, and you bombard it with a photon that is enough and just the right amount to get it to the second excited state. From here, let's draw all the possible transitions and think about what's happening, right? So from the second excited state, from n equals 3, it could jump down to n equals 2. We draw a transition as an arrow, which means it would jump down here, it would lose energy. Does that mean it's absorbing or emitting a photon? emitting. In fact, it's going to emit a photon of this difference in energy, which will then translate to a particular frequency. Now, once it's there, where could it go? Oh, sorry, when it was back in the second excited, it didn't have to jump down to first excited state, it jumped all the way down to ground state. In doing so, it would lose a whole lot of energy, again emitting a photon of a different frequency, the difference in these two energy levels. However, let's say it was back in the second excited state, didn't have to jump. Oh, sorry, once it was in the first excited state, it could jump down to here. So we have three different transitions. It could jump down to the first excited state, jump all the way down, or once it's in the first excited state, it could jump down here, which would be a different difference in energy, which would translate to a different frequency in the emission spectrum.